Good afternoon, everyone, and welcome firstly to all the program participants and all the others who are here to attend this very special event, the ICTS Distinguished Lecture. And it's a great pleasure that we have today Professor László Székelyhidi, who will be, I hope I got that approximately right, to tell us about some of the exciting work in this area. But before that, I just wanted to, especially since many of you are participants here for the first time to ICTS, to give you a glimpse of the institution that you're at and an idea of what we do. So this is, of course, the visual glimpse, and this was actually how the institute was in 2018 when the construction was completed of all the buildings, and we had basically just laid all the trees. But now, I think a few months ago when we took the picture, you can see all the trees have grown remarkably fast. So ICTS also has, I think, greened in these years. So let me tell you about that. But before that, I often highlight this nice watercolor by a mathematician who was here for a program some years ago. And this is he was inspired by our library building, which you may have seen. It is the building with an interesting architecture. If you go inside as well, there is an interesting spiral sort of a configuration, and it's a nice place to also just sit and take some quiet time. So I encourage you to, of course, visit the library, but I also encourage you, if you have yourself some artistic inclinations and you would like to share it with us, we would be very happy to highlight it. By the way, a couple of weeks ago, there was a participant who came and actually was an avid bird watcher and told me that he found 45 species of birds on the campus every day, morning and evening, when he would go around with a camera, and he actually captured many of those. And so again, so all kinds of things, anything you would like to share, we are very happy to welcome it and acknowledge it. But coming to ICTS, it's one of the newest centers of the Tata Institute of Fundamental Research, which maybe you have heard of. So TIFR is now not a single institution out of Bombay, but has many centers, and ICTS is one of the centers in Bangalore, together with TIFR CAM, where Ujjwal and so on are from. So we have also a center in biology. National NCBS is also in Bangalore. But TIFR has multiple centers, and each of them have somewhat specialized mandates, so to say. And ours is a bit patterned on KITP or the Simon Laufer Institute, or MSRI as it used to be, and other such places, but with certain innovations. And the idea is that the central component of our mandate is to organize programs like these, workshops, schools, and other activities, and I'll tell you more about them, and also to interweave them with our own in-house research. And I'll say a bit about that. And finally, outreach too, which we do a lot of. Probably the differences from some of these institutes lie in the nature of the precise mix that we have. We have programs in a number of areas in physics, mathematics, computer science, quantitative biology, climate science, and so on. So it's theoretical sciences, very broadly described or interpreted. And I'll give you examples. But before that, our faculty, so we have a very vibrant and very high quality faculty members. Currently, they are about 35 to 40 in number. There's a PhD program which has almost 120 students, and about 30 postdocs. We don't have any departments. We try to have people who can speak across departments and talk between disciplines. And but we do have somewhat fluid groupings. That was not an intended pun, but yeah, is appropriate for this audience. In the mathematical sciences, we have people working on dynamical systems, PDEs, including Navier-Stokes and related related equations, PDEs, and also with a view to the climate sciences. We have algebra, geometry, mathematical physics, probability theory, and very recently started theoretical computer science, which will again hopefully grow. And many of these things have links with each other, in fact, to the physical sciences, which are currently in astrophysical relativity, condensed matter, stat-mech, fluid dynamics again, quantitative biology, string theory, quantum field theory. But coming to the workshops or the programs, this is just a collage of some of the recent posters from recent meetings that we've had. We have programs organized by anyone in the global scientific community who would like to organize a program here. They have to just participate in our open program proposal. There's a twice-a-year call. It's the middle of the year and end of the year, so very easy to remember the dates. And programs are typically 2 to 3 weeks long. They have a pedagogical component, like in this meeting, aimed at, especially at younger researchers in India to develop their expertise in some of the frontier topics. The programs that are, the proposals that are submitted are vetted by a committee, a national committee with experts in most of these areas. And we spend a whole day going through all the proposals very carefully. And in fact, I'm happy that there's a very significant kind of a response from the scientific community. We get many more programs than we can support. I think the current acceptance rate is about 40%. But we nevertheless we work with the program organizers, sort of tune proposals, and perhaps people resubmit them, etc. So in any case, I like to make the point that this is not a conference center. It's like some of these other institutes. We actively shape the programs. We kind of look for certain kinds of programs. We work with organizers often to build up on previous programs. And as I said earlier, we look for those areas where we feel there is a demand for training people in the subject in India, some exciting new developments. So we have about 35 to 40 per year, and with over 3,000 external participants coming through, there's a large international component as well. And I think it's fair to say that it's become some kind of a hub for the country's researchers for new collaborations and ideas. And this is, again, something I like to highlight, that we have a number of publications which have come out of these programs. So if you find that there's some work that has been started, or your stay here has helped in the carrying out of the work, please acknowledge it in your publication. And there's a standard blurb that the program office, a sentence of acknowledgement with a code number, which I think will help the program office keep tally. And this, of course, makes a big difference when we approach our funding agencies. So I hope you will just remember when you write up a paper or something that has had maybe some contribution from your stay here at ICTS. All our talks are archived, and we have now a large repository of over 7,000 lectures, starting from programs even before the campus was built, so about 10, 15 years of programs. Our YouTube channel has a large number of subscribers and views. And again, for younger people, I encourage you to explore the channel. There's a lot of very nice material there because of the large number of talks by experts that we've had over the years. Just to kind of give some examples of new programs, just a somewhat random list of recent programs. And as you can see, the main thing is the wide ambit of the programs, from things in astronomy and machine learning applied to health and disease, but also in quantum metrology, string theory, trap downs, climate studies, etc. So there's a large set of topics. We also have specialized schools which have been running. There's one on quantitative biology, which we run with ICTP in Trieste. It alternates every 1 year in Trieste, 1 year in Bangalore, and that's been going on for more than a decade. Similarly, the statistical physics school that just got over actually last week, that's something also been going on for a while. And several others, as you can see, which have been quite successful as schools for training people. I also want to highlight, again, for the younger audience, some of these very special lectures that we have, like the distinguished lecture here today, and the Chandrasekhar lecture in the physical sciences, Ramanujan lecture in the mathematical sciences, Turing lectures in biology, computer science, and so on, and several others. Finally, just a word about our outreach activities, which we also do quite a bit of. There's a lot of public lectures and other things which are more standard vanilla outreach, but we also do some more interactive kind of experiments in scientific interactions with the public. We had an online exhibition, an interactive exhibition, or an interactive kind of, I wouldn't say exhibition, more like an interactive sort of a web page through which you could explore the universe at different length scales. That's what we call cosmic zoom. We also have been involved in science pedagogy, working with some of the neighboring schools. And again, something I want to highlight to this audience is something we started the last 4 or 5 years to build a math circle network. This is something I think probably originated in Hungary, if I'm not mistaken, long ago. The idea of the math circles, it was very popular in the Soviet Union and then went to the US and has helped, I think, to really identify and nurture mathematical talent. And this is something we are beginning, I think, in India to sort of grow. And I hope that these math circles, which are meant for children from grade 6 to 12, and it's meant to be open-ended mathematical exploration, not necessarily geared towards an Olympiad or a competition, that kind, but perhaps that will follow, but definitely to make maths more engaging for children and to identify young talent. And I'm happy that we've had some success in that. I think now we have math circles in person in Bangalore, in Mumbai, in Kolkata, Chennai, Bhopal, as well as a couple of other places. And I hope this will spread. And all of you have heard yesterday the news of India doing so well in the chess Olympiad. And I hope the maths circles, I think a lot of that is because of the chess clubs that are all over India now, which wasn't the case even when I was young. But I hope the math circles will do something similar for mathematics, have these sort of clubs where kids who enjoy maths can come together. So anyway, that's just the beginning of this thing. And but if you're interested in participating in this, please go to the outreach webpage and check out the Math Circle header, and you'll find you'll find an email address you can write to if your institution would like to take part. And we have had many ICERs, IITs participating in this and partnering with us in this. So please let us know if you're interested. Okay, so that's it from my part. I have come in the way of your hearing the featured talk today. So it's, as I said before, I'm very happy that Professor Székelyhidi traveled and spending time here at our workshop. And I think the distinguished lecture, the ICTS distinguished lecture, as you would see, is something that's a very special event where a distinguished scientist gives a colloquium level talk. And I can see some of you who are not in the field either here. I'll invite Professor Ujjwal Kole now to give a scientific introduction to Professor Székelyhidi and then proceed with the lecture.
Okay, so thank you, Rajesh, so for organizing this talk in ICTS. And also thank you, László, for kindly accepting our invitation. For many of us, I think László doesn't need any introduction. But since this is meant for a broader audiences, so let me say a few words. So László studied at St. John's College, University of Oxford, and defended his PhD at the University of Leipzig in 2004. So he worked at ETH, and he was a member and later a distinguished visiting professor at School of Math of Institute for Advanced Studies in Princeton. And currently, László is a professor and also the director of Max Planck Leipzig. The main research interests of László broadly evolves around partial differential equations, calculus of variations, and hydrodynamics. So he has several fundamental contributions in these fields. So let me briefly highlight one of his recent contribution in fluid mechanics. So jointly with Camillo De Lelis, fortunately he'll be also with us in a couple of days. So they came up with this groundbreaking idea of including convex integration technique in fluid dynamics problems. And in fact, they introduced a very powerful tool which led to the resolution of the flexible part, or rather the hard part of the celebrated Onsager conjecture. And remarkably, these techniques has been successfully implemented to establish various other results, such as non-uniqueness results for Navier-Stokes equations. So László has received many awards. So he won the overall Falk Prize in 2010, Leibniz Prize in 2018, which is considered to be most important research funding award in Germany. In 2019, he was elected a member of German National Academy of Sciences. In 2022, he became a member of Hungarian Academy of Sciences. He was also an invited speaker at ICM 2014 in Seoul. So László will give a series of talks. In fact, so today he will start with something very basic, I guess, and understandable to everybody. So today he is going to talk about dissipation and mixing from turbulent flows to weak solutions. So Professor Székelyhidi, stage is all yours.
Thank you very much, Val, for this kind introduction, and also to Rajesh for the invitation to this wonderful place. I'm enjoying it. It's a few days so far, and it's also my first time in India, but I hope it's not the last. As was mentioned before, this is more a colloquium style lecture. So I will give a very basic kind of gentle introduction to the topic of turbulence, dissipation, and also the Onsager conjecture. But for all the participants at this 2-week workshop, I don't want you to get an overdose of Onsager, so you can think of this as a gentle introduction, an advertising spot to what's coming. For those of you who are already expert in the subject, it's an invitation to take a step back, view the field from far away rather than the technical details. And for all others, it's just an invitation to learn more. So here we go. How is it that there are so many minds that are incapable of understanding mathematics? Is there not something paradoxical in this? Here is a science which appeals only to the fundamental principles of logic, to the principle of contradiction, for instance, to what forms, so to speak, the skeleton of our understanding, to what we could not be deprived of without ceasing to think. And yet, there are people who find it obscure. And actually, they are the majority. That they should be incapable of discovery, we can understand. But that they should fail to understand the demonstrations and proofs expounded to them, that they should remain blind when they are shown a light that seems to us to shine with a pure brilliance, it is this that is altogether miraculous. And yet, one need not have great experience of examinations to know that these blind people are by no means exceptional beings. We have here a problem that is not easy of solution, but yet must engage the attention of all who wish to devote themselves to education. These lines were written by Poincaré in 1908 in a book called Science and Method. I recommend everyone to take a look at this book. It has very deep thoughts on different aspects of mathematical education and research. And in a sense, Poincaré in this essay is not just talking about education in high school, but also education in the sense of talking to colleagues in research. And the problem that he's referring to in this essay is the problem of proper mathematical definition. How to define objects in a way that they make sense. And he identifies, later in this essay, essentially three important criteria. The first one is, of course, mathematical rigor. You have to have a rigorous definition in order to be able to work with it. On the other hand, the definition should be intuitive. You should know what you're talking about. And descriptive, in the sense that the definition should reflect then, or from the definition, you should be able to derive properties of the object that you see, that you expect. And thirdly, and this is going to be what I want to focus on for a few minutes, it should not create monsters. Now, what Poincaré means by monsters is that, he explains that a few pages later. Logic sometimes breeds monsters. For half a century, there has been springing up a host of weird functions which seem to strive to have as little resemblance as possible to honest functions that are of some use. For instance, no continuity, or if they have continuity, no differentiability, and so on. Formerly, when a new function was invented, it was in view of some practical end. Today, they are invented on sole purpose to show our ancestors' reasonings at fault, and we shall never get anything more than that out of them. So he refers to a very specific monster at this point. This monster was born in 1872 at a lecture in Berlin given by Weierstrass. And the monster looks like this. Don't be scared. 1/2 cosine 3 pi x plus 1/4 cosine 9 pi x, and so on. Or more modern notation, more generally, the sum of b to the n cosine a to the n pi x. And these numbers a and b, so here it's 1/2 and 3. So Weierstrass showed that if ab is bigger than 1, actually he showed 1 plus 3/2 pi, which these numbers don't satisfy, but it was later removed. Then this function is continuous, but nowhere differentiable. So this was a big problem, especially for French science at that time. We're speaking 1908. or sorry, 1872. It was just after the French lost the war against the Prussians. And now they're even kind of banging against the theorems of great French scientists. So one of the classical theorems at that time in textbooks, French textbooks, was by Ampère. The theorem of Ampère from 1806 said the following: every continuous function is differentiable at least at some point. In fact, it's not differentiable only at certain values, certain isolated values. Certain values particuliers et isolés. So this was clearly a counterexample to that. And in fact, so Charles Hermite, who was at that time a member of the French Academy of Science, he was a Grand Officer of the French Legion of Honor. So in modern terms, we would say he was an influencer of his time. Wrote in a letter to Stiltjes, I look with horror and pity at this sorrow state of non-differentiable functions. So they had a very bad opinion. These are the monsters that Poincaré was talking about. And his point was, you know, a definition should be useful for something. And somehow this workshop, and also in this talk, I will talk about this. These functions are useful for something. They are of some practical use, let's say. Practical in a more generalized sense. So let me turn to hydrodynamics. Now, there's a nice saying which goes back to Cyril Hinshelwood, Nobel Prize chemist from the 1950s, who said about hydrodynamics the following: the hydrodynamicists, people, the community working on hydrodynamics, can be roughly classified in two groups. There are those who observe properties of fluid flow that cannot be explained, and there are those, these are the mathematicians, who explain properties that cannot be observed. And to be fair, he was talking about the state of the art of the 19th century, but I think it's good to keep this in mind as a warning. So, and in fact, you don't have to look far to find such properties. The most basic problem in fluid dynamics, which was probably the first one that people thought about, is the following. If you have a sphere of, or ball of radius L, that is in a uniform stream of some fluid with density rho and speed u, what is the force acting on this ball? That's a very classical question. And already, so what is F? The force of resistance. And already Newton, in his Principia, wrote in, is it 1687, that where he derived that F should be proportional to rho times L squared times U squared. Okay, nice. Well, of course, this was based on dimensional arguments, let's say more from a physical point of view. And roughly 100 years later, from first principles, D'Alembert, this was 1752, derived that at least in the, let's say, unphysical case, that the internal viscosity of the fluid is 0, then F is 0. Okay, that's the famous D'Alembert paradox. And another 100 years later, Stokes. This is sort of unphysical. So Stokes looked at the Navier-Stokes case, fluids with viscosity, derived the formula, which is very specific, 6 pi rho nu L U. So you see, this is when people talk about scientific consensus, scientists all agree on certain issues. This is not the case. And it turns out that, in fact, all of them are right. But the key difference is what is known as the Reynolds number. It was already mentioned, and it will be mentioned more often. For this setting, it's U times L divided by nu, the viscosity. And this is a dimensionless number, which essentially gives you some a quality of whether the fluid is turbulent or not. So for instance, if the Reynolds number of a flow is roughly 1, then this would be laminar. And then essentially Stokes is correct. But if the Reynolds number is of the order of 10 to the 6, this would be a turbulent regime, then Newton is essentially correct. And I want to emphasize again, so Newton's derivation is very simple. It's a small paragraph in the book. D'Alembert and Stokes is more complicated and based on first principles. So it's really based on analyzing the underlying partial differential equations. The incompressible Navier-Stokes equations in 3D. So it seems that the PD techniques, the first principle techniques, are able to recover properties of laminar flows, but not so much properties of turbulent flows. And so that's somehow the challenge here. And the difficulty in the challenge is, of course, there's this Reynolds number, which is large. If I keep U and L fixed, large Reynolds number means small viscosity. So I'm kind of looking at the situation when this nu goes to 0. Okay? And the question is to understand this limit. And what makes this problem really difficult is that this is what is known as a singular limit. Okay? And what is a singular limit? I like the description by Michael Berry. There's a nice article by him on what is a singular limit. And he describes this as follows. So imagine you have an apple, and you take a bite into this apple, and then you see a little maggot moving in the apple. Well, that's kind of not a nice situation. But it's much worse if you would only see half a maggot. And if you would see 1/4 of a maggot, it would be even worse. Okay, and so on. The situation gets worse and worse. But if you don't see a maggot at all, it's fine. Okay, there is a singular limit. So the question concerning the PDE context is how to formulate a theory of solutions which does not describe this laminar regime, but describes this turbulent regime. Okay, so in some sense, formally we would be looking at the case of the Euler equations, but we want to kind of think of the situation where you've swallowed the whole maggot, not the case when there's a maggotless apple. And so this brings us to weak solutions. Now, weak solutions, you might think is a kind of modern invention, but it's actually as old as PDE theory altogether. It was already a subject of intense discussions for the case of the 1D wave equation. So D'Alembert let's get my dates right, 1747 derived the one-dimensional wave equation. Okay, and also derived the general formula, which is just the sum of a wave going to the right and a wave going to the left with constant speed c. Okay, that's the general formula. But of course, he said, well, since I have two derivatives here, this f and g has to be twice differentiable. Otherwise, of course, this doesn't make sense. That's what D'Alembert said. Euler, on the other hand, said, well, you derive the equation without assuming that, any differentiability, so it should be okay. Euler didn't see the problem with having a non-differentiable f and g. And the problem really boils down to the following question. If you take a string and say an initial condition which is like this, it has a jump in the derivative. This still gives you the sum of two waves, which are half the size, one going to the right, one going to the left. But the question was that, and there was an intense discussion between D'Alembert and Euler, how do you define the force at this point? The way the wave equation is defined is by defining the force, the elastic force, and that's causing the wave to move up and down. But how do you do it here? Because the force is proportional to curvature. There's no curvature here. And so it was an interesting long discussion, but this was eventually resolved by Lagrange in 1760, who basically argued the following way. Well, this PDE, the way you derived it, it's a continuum model. It's not a pointwise. The way it's derived is that you take little intervals of the string and compute the average force on those little intervals. And then you let the size of the interval go to 0. So as a continuum theory, it doesn't make sense to ask the question, what is the pointwise force? It's always a kind of average force over infinitesimal intervals. And then you can actually define the force here. So in this way, Lagrange actually came up with the modern definition of weak or distributional solutions. There is another version, another way to resolve this, which is, of course, Fourier series. It was later, early 1800s. I think I've got 1807. Which is that if you just write the solution as a sum of eigenwaves, sine 2 pi kx, where these are functions of time, then you can just plug that into the equation and formally equate coefficients and obtain ODEs for the coefficients. Okay, that's a classical thing to do, and and that still makes sense even if you have this sort of initial data. So you can replace this PDE by infinite set of decoupled ODEs. You can solve each one of them. There's no issues. So this method for going back to hydrodynamics was applied to the the Navier-Stokes equations by Leray. This is the Leray definition of weak solutions. And the Fourier method was applied by Onsager to the Euler equations in his paper in 1949. So both of them are used in the context of hydrodynamics. Now this is good. We have a class of solutions where we are not anymore in this laminar regime, but at a price. Because in 1993, it fits here, 1993, Scheffer showed that if you just take this as the definition of weak solution to the Euler equations, you can have completely unphysical solutions. You can have solutions which are, say, u is 0 for some initial time, then it's not 0 for some interval of time, and then it's 0 again. It contradicts not just determinism or uniqueness of the 0 solution, also energy conservation, or at least dissipation. So it's clearly unphysical. This is what Cédric Villani refers to this as the Scheffer monster. The the Scheffer monster, in analogy to the Weierstrass monster. And that, of course, then leads to the question, you know, we have to look at more properties that we have to restrict the class of solutions that we want to consider. We have to look for some selection criteria and so on. So this is the question of what Poincaré refers to as you have to have an intuitive definition which is descriptive. It should not lead to monsters. Okay, so what kind of additional properties do we want to look for? Now, an important concept that I want to spend some time talking about is energy cascade. So if I follow Fourier's Ansatz and write the solution, the velocity field as a Fourier series, a complex Fourier series. So here, in order to represent a real function, I have to have this condition and divergence free this condition. Then the Euler PD, Euler, is equivalent to saying dAk dt plus nu k squared ak equals a sum, I, and then it's a sum over L, a k minus L, scalar product with k, times AL minus k scalar product AL divided by k squared k. So this part, sorry, this is Navier-Stokes. So this part is just a heat equation where you see that analogous to what you would get in the wave equation, you've decoupled set of ODEs, but this part is quadratic in A, and it couples them. And this coupling leads to a transfer of energy from one mode to the other. And if this transfer happens at a certain self-similar way, self-similar mechanism, one speaks of an energy cascade. Energy because the modulus of AK squared is essentially kinetic energy. And so to illustrate this a little bit, I learned a nice sort of coupled wheel model from Alexei Cheskidov. So imagine sort of lots of wheels, maybe of decreasing sizes. Maybe they should be geometrically decreasing sizes, but that's difficult to draw. So these represent the different Fourier modes, or more precisely, the dyadic groups of Fourier modes. And they are coupled. So if I would have just the wave equation or the heat equation, each one would just rotate in its own speed given by the initial data, by its own law. But they're coupled. And the coupling is sort of like a clutch, or like a bicycle, which has two wheels. But now you can have infinitely many wheels. So I like to think of this as the Hilbert bicycle, like the Hilbert Hotel. Okay, so let's call this the Hilbert bicycle. Okay, and you're sitting here with the pedals. So in a sense, in the Navier-Stokes equations, each single wheel has a certain amount of dissipation given by this term. But if the size of the wheel is still too big and the dissipation, this nu, is very small, it's negligible on the large wheels. So there's a certain size wheel, let's say somewhere here, of size or length scale, which is proportional to nu to the 3/4, just by dimensional analysis to get the lengths. This is the length scale at which you will start to see the viscosity. So we can imagine replacing the Hilbert bicycle by a finite many-wheel bicycle where you just put a brake here. Okay? So this one is, let's say, a faulty wheel or something, and it breaks. And the question is, what is the effect of this small wheel braking when you're sitting here pedaling? What is the rate of dissipation given by the little viscosity in a turbulent Navier-Stokes flow? Okay, and the fundamental fact in turbulence is that the rate of dissipation, of energy dissipation, is usually denoted by epsilon, is independent of nu as nu goes to 0. I mean, as Reynolds number goes to infinity. Okay, so this is something that's already reflected by the Newton formula. Rate of dissipation is, of course, related to the resistance. And in Newton's formula, there was no viscosity, no Reynolds number. So that's already reflecting this fact. But there are other ways also to measure this, of course. And this fact is sometimes referred to as the 0th law of turbulence. I learned this from Srinivasan. 0th law. It's so fundamental, it's even more important than the first law. And one of the challenges now, when we go back to the question of having a theory of weak solutions that reflects real life, is to come up with a theory of weak solutions that reflects this 0th law. Okay, now we can get some scaling out of already this very simple picture in the following way. So the mechanism that will kind of explain this fact is that no matter how long this sequence of wheels is, there is a sort of self-similar or dimensionally consistent mechanism, same mechanism that transfers energy at a certain rate from here to here as from here to here. Let's say self-similar mechanism. Okay. So if you accept this hypothesis that there is a self-similar mechanism, you can compute the rate at which this energy transfer happens. Now that can be done by just dimensional analysis. For instance, if you have some wheel of length or radius L, length scale L, and suppose it has energy, kinetic energy EL, which is sorry, let me think about this. What did I want to say? Well, that's what I wanted to say. So, in fact, there is nothing. So okay, there is a self-similar mechanism. The question is in a sort of statistical steady state. So there's constantly, you're turning the wheel by pedaling, and constantly there is some energy which is being moved along this sequence of wheels until it's dissipated at this thing. But then what is the energy sitting on each wheel? That's the question. Okay. And so that has to be something that only depends on the length scale and this epsilon. And then by dimensional analysis, one gets this. That's the only dimensionally consistent expression that you can form from dissipation rate and length to get kinetic energy. Okay. Now this is typically in physics papers, people like more the Fourier version. So this length scale is physical length. K would be wave number, but this is the same as epsilon to the 2/3 k to the minus 5/3. Roughly speaking, this minus 5/3 is the Fourier transform of this 2/3. Okay, and this is known as the Kolmogorov 1941 law, K41 theory. Okay, 5/3 law. 5/3 law. So this is just hypothesizing. So we are assuming that there is this sort of self-similar mechanism, and we are also assuming that the energy only depends on these two quantities, nothing else. That's assuming a lot of symmetries on our system or on the turbulent flow. But then we get this. And so this is already a very specific number. Just to form the connection to Weierstrass, you might notice, since kinetic energy is like velocity squared, this L to the 2/3 is roughly speaking saying that we are looking for a velocity field. It depends on time also, but time doesn't appear in this whole picture. A velocity field which is of the form, well, there's epsilon to the 1/3, and then k to a to the minus 1/3 cosine a, sorry, 1/3 n, a to the n pi x. Okay, just to form the connection with Weierstrass. Okay, so B is a to the minus 1/3. And a is bigger than 1. Just as a kind of analogy, like what kind of functions are we speaking about if you have this energy cascade, this energy, this power law spectrum? And this is the sort of functions you're looking at. And a small exercise that you can probably do by the end of this talk is to show that U is Hölder continuous of exponent 1/3, which means differences in velocity scale like distance to the 1/3. This is the same Y. Okay. Sorry? Thank you. The K is N. Yeah, thank you. Yes. Okay. So already this very cartoon picture gives us a way of asking real questions in mathematics about the fundamental equations of fluid dynamics. Here are 3 questions. The first one is one that you already heard this morning by Hyunju, the Onsager conjecture. And then there are 2 more questions. Okay, questions. The Onsager conjecture, which is, okay, essentially it's proved. Onsager conjecture is about the Euler equations in 3D.
We were trying to explain the zeroth law from the scaling or not? Or
yes,
okay.
yes. Sorry, I messed up my argument. Basically, no. Sorry, I was assuming the zeroth law. It's a fact of life. But if I assume that for my solution or for this simple model, then I deduce this scaling.
Zeroth law or?
Not yet. Not yet, but that's a good point. That's question number 2. So question number 1 is just to come up with a theory of weak solutions for 3D Euler that shows that scaling, okay? And has anomalous dissipation. So has dissipation of the energy. Okay, that's the interpretation of the Onsager conjecture. So describe, so in some sense, describe the limit state nu equals 0 when you swallow the whole maggot, okay? Not the one where there's no maggot in the apple. And the second question, which is the question that you're asking, is to actually give a justification of the zeroth law. So which means you have to come up with a theory for the Navier-Stokes equations. Okay, again in 3D, where you can describe this limiting process. It's not just the limit state, but describe the limiting process as nu goes to 0. So one particular question you can then ask is whether it is possible for some situation, let's say initial data, or you add forcing on low modes like this, riding the bicycle and pedaling the low modes, to prove that the energy of the fluid, so energy of the solution at time t, which is given by this. Now, by the equations, this is equal to the energy at time 0 minus the dissipation, cumulative dissipation. Okay, so this is what happens for the Navier-Stokes energy identity. Now that's not even known to be true in general. Okay? We only have an inequality, but that's not the point. The point is to show this is the dissipation. So the dissipation rate is nu times this space integral, and to show that the limit, or liminf in the best case, of nu going to 0 of this nu times the integral in time, integral in space of this quantity is not 0. So this could be called the dissipation rate. Sorry, total dissipation depends on t. Of course, you can then ask the same thing. So this should be positive for all t. And then you can ask questions like, how does it depend on t? It should be positive for all t. Okay, and that would be one possible question, which people are thinking about. And the more difficult question is to actually describe the limit. Prove that the limit as nu goes to 0 in whatever sense. I don't think people have an exact way of thinking of this limit so far, of u nu is a weak solution of Euler, which should then agree with whatever solutions we have here. Okay? Maybe the ones we have here so far are not the right ones. Okay? But that's the general way of thinking. If you want something of practical use, to cite again Poincaré, these would be the questions. And we don't know how to answer this one. As I said, and this will be subject of several lectures here, we know how to answer this one. And we know how to answer a baby version of this one. And that's what I want to speak about also in the next lectures. So this is a sort of scalar version passive scalar anomalous dissipation. So here the zeroth law, okay, so let's say version of the zeroth law is about dissipation of the scalar variance. So here we have some scalar, which could be density, it could be temperature, it could be other things, which is advected by the flow and it's diffusing. And there's some diffusion coefficient. And what is the flow? Well, this U should represent the turbulent fluid velocity. Okay, and then it's a question of what we mean by that. But here you have an analogous balance of energy, which is in this case not difficult to prove. And then the analogous question of this one would be, say, 1 prime, show that the lim-inf as kappa goes to 0 of kappa times this integral is positive. And then again, ask questions about how it depends on time and so on. And then, okay, so what is U? So U could be many things. It could be just a kind of a random velocity field modeling turbulence, turbulent flows. So this is what is known as the Kraichnan model. But it could also be a weak solution of Euler. Okay. And ideally, it should be a solution of Navier-Stokes with viscosity related, of course, then to the kappa. Okay? Big solution of Navier-Stokes. Viscosity nu. Okay. Now, I don't think so. So, okay, I can tell you that what we can prove is, well, it's not a lim-inf, but a lim-sup, okay? But what we can prove is that, okay, so the expectation for small t is that it's t to the cube. Is that right? Yes, t cubed. This is related to the paired dispersion. The expectation for large t, I'm not sure, but it can't grow indefinitely because there's a finite total energy, so here. So I would expect that it just stays constant after some time. But the interesting question is what happens for small t. The same here. In fact, yeah, it's not that this one, we can prove this one. And for small t, we have the t cubed, essentially. So these are questions that arise from this, I would say, very simple but very compelling picture. But it comes at a cost. As the Scheffer monster, you have to think about monsters all the time. And the monster here is that in this whole scaling argument, I didn't really ensure or use the information that the energy is moving in this direction, which is called the forward cascade. So I was saying, okay, yes, I'm pedaling here, but suppose I'm not sitting on this wheel, I'm sitting on this wheel or this wheel. And actually suppose that there is an infinitesimal person. So let's say we are back to the Hilbert model, an infinitesimal Maxwell demon, which is riding Hilbert's bicycle to complicate the picture, okay? And then the energy is going this direction. So then Hilbert's bicycle is moving, but you don't see why. Energy is being created. Now the mathematical, the theorems that correspond to this is non-uniqueness. Like the Scheffer monster is an example of this, where energy is being created at some point, apparently, in the weak solution. And the reason for that is that there is a backward cascade. This is something that's, maybe we can avoid the Maxwell demon, but it has an effect of practical importance. I have still some time, right? And this is known as the butterfly effect. And it appeared in a paper of Lawrence, but not the famous one from 63, but from the one, another famous one from 69, which is less well known. This is Lawrence, 1969. Okay, which again, a wonderful paper. I recommend to read it. So in this paper, which is entitled Predictability of Motion on Many Scales, he is asking about the range of predictability. And he's thinking about atmospheric climate science, more meteorology, let's say. So what he calls the range of predictability is essentially the time within which errors of predictions do not exceed some kind of predefined value. So it's still acceptable. Whatever simulation you have, it gives an answer that's still within a certain acceptable range. And the question he's asking, well, if you have a system on many scales, like this system, which is in this cartoon picture, now we can think of these wheels representing different motions in, let's say, the atmosphere. You have large motions by, say, Rossby waves on scales of 1,000 kilometers. You have thunderstorms, which are more scale of a couple of kilometers, and so on. And they're all interacting via a nonlinear interaction, which is here modeled by these chains. And the question is, suppose I make some small error on the small scale. How much is that going to affect my range of predictability? And it's precisely because of this inverse cascade. Suppose on this small scale, I make a small error in my observation, or it could be in my simulation. If there is an inverse cascade in my system, then it's going to amplify. So that means, suppose from this scale, it amplifies at a certain rate to this scale, then, self-similar way, it will amplify eventually to this, and eventually it will be a big error, okay? Now, on each single scale, if you have, so on scale L, you have, say, a range of predictability tau L, which is just a time scale. So the time scale has to be like L divided by the typical velocity, which is L times the kinetic energy to the -1/2. Then the question he's asking is, suppose you are on a big scale, capital L, which is 2 to the n times little l. After what time will the error that I make on the small scale observation become order 1 on the large scale? Assuming that my system has scales on all dyadic powers of L, of little l. The answer is simple. The time it will take for this error to propagate up is the sum, right? It's 2 to the little l plus tau to the 2L, all the way tau to the capital N, to the N L. Okay? So it's this sum. From 1 to N, 0 to N. Okay? And so since this tau is now given in terms of the energy spectrum, we can plug in that value, that scaling law, and see if this sum converges or not. The point is, if it converges, it means no matter how small my initial error was made on what small scale, in finite time, fixed finite time, it will reach the large scale. Basically meaning I cannot make my observations precise enough. Okay? There will always be a certain finite size error. And this happens if you have this energy spectrum of 3D turbulence, okay? Then this, so in that case, tau L is just scaling like L to the 2/3. Okay? So it converges, which would be really bad if our atmosphere actually had an energy spectrum of 3D turbulence. And we just couldn't make any, and there's a very nice simple computation that he gives just to illustrate this, that if you suppose, let's say some typical values. If you have a weather system model where on like on a scale of 1,000 kilometers, the range of predictability is 5 days, which would be a typical weather model. Now maybe it's even more, but this is from 1969. Then if you had this scaling law, the 5/3 law, then the range of predictability on 1 kilometer would be 15 minutes. Okay, just by the scaling. Okay, so that means if you would, and then you can continue that. So suppose that now you build with lots of money weather stations that are so accurate that every meter exactly the value of the weather quantities, temperature, pressure, so on. It would only improve your range of predictability by a couple of minutes. It would be completely worthless. It's an interesting, so that's why people in geophysical science always think of the energy spectrum of, and of course, luckily, the atmosphere is not governed by the 3D Navier-Stokes equations. On these large scales, it's governed by quasi-geostrophic equations which have an energy spectrum like 2D Euler. And that scales differently. That scales like, I wrote it down somewhere, like L. E to the L is L. Okay? Sorry, L squared, which is the K to the -3 spectrum. So I just like right here. The QG and 2D Euler, this EL would be like L squared, or A. Usual notation is K to the -3, where this tau L would be order 1. It's sort of the borderline. But you also saw Sid Mishra showed these simulations in the last talk of 2D Euler with the Kelvin-Helmholtz instability. So 2D Euler, and it looked like he was showing precisely this, that no matter how good your resolution is, you will not be able to improve accuracy. And that's related to the fact that it's the energy spectrum of the initial data that determines this picture, not the statistical steady state. And the initial data being discontinuous, it's again, the spectrum is more like, I think it's, I computed it, it's L, where this tau L is L to the 1/2. So again, it converges. So that explains a little bit why even in 2D simulations, where you start with a non-smooth initial data, you cannot improve the accuracy by increasing the resolution.
Clarification. When you say 2D Euler, it's one space, one time, or two space dimension?
Oh, two space, one time. Yeah. Oh yeah, I'm sorry. I'm referring to a talk which many people here didn't attend, but maybe you would would like to attend the later talks of the workshop. So coming back, so this is the butterfly effect as described by Edward Lorenz. And now coming back to the passive scalar zeroth law, you can think of a version of this argument also in this advection diffusion equation in the following way. Imagine that I have this, again, this picture, which is representing the different eddies in my turbulent velocity field. So this is fixed, okay? And now the motion of this velocity field, the advection, leads me to kind of move the energy or this variance of the scalar from one scale to the next scale at a self-similar rate. It's not and then the question you should ask is, how long does it take until this scalar feels the diffusion, which is again for small kappa, it's something that is maybe lying somewhere here. And that's precisely the same question in the other direction. The Lorentz question was about the backward cascade. How long does it take for this small perturbation to reach here? Now I can ask the question backward for the forward cascade. How long does it take for a scalar to reach this scale, where it will be sort of eaten up by the diffusion? So it's the same scaling argument that will tell us that in 3D, because we have this spectrum, I will have convergence. So in finite time, I will feel the diffusion. In 2D Euler, or even in 2D turbulence, in 2D Navier-Stokes turbulence, I have this spectrum, which means it will take infinite time. More precisely, because you have these ones that you're adding up, okay, in this sum, it's a logarithm that comes out. So essentially, what you will get is that the time it takes for diffusion to kick in is of the order logarithm of kappa, okay, which is precisely the estimate that was recently obtained by, okay, I'm messing up my board, by Bedrassian, Blumenthal, and Punchensmith. So they considered 2D Navier-Stokes forced randomly in a statistical steady state, and considered then the how long it takes for diffusion to kick in. So how long? Well, how long do you need to do this integration to see diffusion? And it's precisely the logarithm in time, bigger than some number, say 1/2, something like that. Okay. Before that, you don't see it. Okay. And now, again, coming back to the case where we have 3D turbulence, the simple scaling tells us that we should see anomalous dissipation, we should see this effect, and that's essentially what we can prove. Now I'm probably running out of time. I don't know when I started, but whenever I want, okay. So, yeah. I will finish very soon. So what we can prove is joint work with Jan Burczak and Bian Wu in Leipzig. We can prove that for any beta less than 1/3, there exist velocity fields which are Hölder continuous with exponent beta in space and time, and they are weak solutions of Euler. such that for all initial densities, which are H1, they need to have a little bit of regularity. They need to have a length scale and average 0, integral 0. The lim sup as kappa goes to 0 of T of this quantity is bounded below by a constant that depends on the length scale of the initial data, which you can think of as the ratio of the L2 norm of the gradient divided by the L2 norm of the function times essentially the minimum of 1 and T to the 1 over 1 plus beta. Okay, so if it's, is it 1, 2? So it should be 3 if beta is 1/3. Okay, and I will talk about how to prove this and what are the methods to prove this in the next 3 days. Just to give one glimpse, so one key idea is related to another cartoon way of thinking about this sort of effect, this anomalous dissipation. And it's also something that pops up when one is looking at the Kraichnan model or random models. So if you imagine that your velocity field is comprised of some sort of nice deterministic flow plus a random fluctuation, so this is, let's say, macroscopic flow, and this one is random fluctuation, small scale, like the velocity fields that Mario was talking about. Then the traditional way to think about this equation is to consider expectations and try to derive an equation for the expectation of rho. And this one will be something that has this form. These are all linear terms, so you can just take the expectation. And then there is this term where you have this product. And the physics approach to this is to say this has the form of some sort of additional dissipation, diffusion, okay? Where this kappa T, now it's not time, it's turbulent or eddy viscosity, maybe I call it kappa bar instead. It's called eddy viscosity. It's a sort of apparent viscosity or diffusion that you see from the effect of this product. Okay, and then if you assume that this is what happens, it's clear that even if this kappa goes to 0, there is still this kappa bar. So you are left with some diffusion, and that's a very simple explanation of why you should expect this. But then the question becomes how to prove this. And this is the business of homogenization. And the homogenization has a long history, but the first application of homogenization to this particular set of questions was a recent paper by Armstrong and Vicol, where they constructed a 2D velocity field like this, but it's not a weak solution of Euler, which has this property. And what we did is to refine that technique and apply it to weak solutions of Euler. So that will be the topic of the next 3 lectures. And this is sort of, I would say, our current understanding of this set of problems. And so coming back to Poincaré, I just want to emphasize that, you know, there's lots of problems one can ask in this context of weak solutions. So for instance, another way, which is also, of course, physically relevant, another way of thinking of this kind of questions of anomalous dissipation, which is the one emphasized by Hyunju's lectures, is you have a certain PDE, which has a conservation law for smooth solutions, but then for non-smooth solutions, the conservation law is not valid anymore. Where is the critical line between smooth and non-smooth? That also has a very large history, this kind of question, and it's very relevant. But I want to emphasize that it's important, at least in my research, to, you know, think of the, you know, try to always connect back to experiments and the real physical world, so that Henschel would not say we are still kind of explaining things about fluids that one cannot observe. Thank you very much for your attention.
So thank you, László, for this wonderful talk. And as a token of appreciation, we would like to present Professor Dupakun.
A small memento.
Thank you very much.
A sweatshirt and a mug from ICTS.
Thank you very much.
Thank you very much for a wonderful lecture.
Thank you.
Yeah, so any quick questions or comments?
Sorry? Yeah, how is Hölder continuous defined? It's the it's ux t minus uys is bounded by some constant times x minus y beta plus t minus s beta.
That you had, is that equivalent to proving this Newton's force law that you wrote in the beginning, or that's different?
No, it's not equivalent. The Newton, yes. The Newton law, proving that also requires to, I mean, all of these questions that I wrote down were without boundaries. These are in, you know, periodic setting, or you can also consider them in a full space. But for the Newton problem, you need to think about boundary layer when in turbulent flow around this and the separation. And I think the state of the art is much worse in that business. So that one will be, you know, several steps further down the road.
So you were stepping back from the Navier-Stokes to this passive scalar to try to address some of these questions, and there you had this U put in as a sort of a background, so to say. But I was wondering, are there maybe not directly connected to Navier-Stokes, but other nonlinear equations which are integrable? I don't know, KdV type equations, or nonlinear Schrödinger equations, or some things where the similar phenomenon is there, that it seemingly has energy conservation, but there is a class of maybe solutions which are dissipative, and there, because the underlying equations are in a sense integrable, at least in some category, perhaps that question can be analyzed a little more concretely. Is there any, I mean, I'm speaking as an outsider.
Yeah. No, it's a good question. I don't know of many integrable PDEs, except the 1D cases that you mentioned. One that maybe comes closest is 2D Euler. The 2D Euler equations have a integrable structure, even if it's not really clear if it's integrable in the formal sense. And there, the question An interesting question is to understand the long time limit. So there, it's not a question of weak solutions with weak regularity. We know that already in a pretty large class of solutions, we have well-posedness. You take some initial data, and you have for all time a uniquely defined solution, which conserves all of the for instance, the vorticity which is a scalar, is just rearranged. It's conserved, and all functions of the vorticity are also preserved. So it's just a rearrangement, kind of mixing. But what would people, and that's a nice situation because it's just 2D, so you can also have nice numerical simulations. And you see that, that you have an inverse cascade, even if you start with some sort of pretty wildly oscillating vorticity. After some time, the vorticity will kind of arrange itself into one positive and one negative blob, which are kind of just circling each other. And there's a connection to, so there's a statistical mechanics approach to this, which was also developed by Onsager. I think it's even in the same paper, that basically says, okay, there has to be this statistical steady state, and it's given by, you can get it from looking at the entropy. Essentially, it's because you can have a model where it's not a continuum flow, but a finite number of vortices which are just circling each other. So it's a finite dimensional dynamical system, and there you can already ask this question, and I'm not even sure that one is completely resolved. And for 2D Euler, it's even open to prove, there's, so what are the final states as time goes to infinity? What is the set of possible limits? It's a very interesting question.
So it's a quick. So 1D Burger's equation would be a little too trivial, or that?
1D Burger. So I think somebody is not here. Maybe he's online. So I'm not such an expert on burgers. I just know that Uriel Frisch liked to call it burgulence, not turbulence, because it's about something else. I think you can ask the same questions, but I think the effects are different because Burgers is very much dominated by the formation of shocks. And that's a different effect. That's something that you may see in compressible flow at a high Mach number, but not, it's a different effect. I think, so here, these velocity fields are highly oscillating, but the oscillation is sort of spread out everywhere in space. Even if there is intermittency, it's sort of spread out everywhere. In Burgers, the irregularities would be concentrated on these shocks. I would say it's a different business, but somebody might disagree.
So regarding these oscillations, do we have any idea of like how irregular they are? Like for instance, is the function out of the BV class or some kind of intrinsic structure of the solution? These ones, these turbulent ones? Yeah, the turbulent flows. Like how you're asking how regular they are? Yeah. Yeah, that's, it's basically given, so one way to measure that is by just this law, but this is essentially equivalent to being Hölder. Or if you are going to be more, this is the simplest case. More complicated cases what Hyunju is talking about in her lectures, which are intermittent. So instead of looking at this type of regularity, which is uniform, in the sense that it's supremum norms, there you measure things in an L3 average setting, Bessov spaces, and those could also correspond to the same energy spectrum. But these are technical details, and I'm going to
talk about some technical details in the next lectures, but everything that I don't mention, Vikram behind you will have to talk about in his lecture. Thanks.
So online, any questions? Okay, so it seems like there are no more questions. So let's thank our speaker, László again.